Hey, VC students, this is going to be something that's a little bit out of order from where we're at in your notes, but we're going to have you turn ahead to page 57 or day 57 in the packet because our next thing on our agenda is to take a quiz tomorrow, and at this point, we should probably be reviewing for the quiz. So everything in this lesson that I'm about to do with you is review. You could hit pause right now, do day 57, and then check with me next time I see you if you really wanted to. So in fact, this video should be quite short. If you look at the top here, these are a list of all the topics that I would really be familiar with and ready to take a quiz on next time you're in class. But before we do that, I'll do some of these practice questions with you. And this way you can check with me before you take a quiz if you have any questions here. So let's take a look at just evaluating this definite integral to start from 0 to pi of sine squared x dx. In terms of our techniques for integration, we might be thinking, since we've done so much u substitution lately, that we should do u sub, but there's not really a good u sub, because if I let u equal sine, du would equal cosine, and I don't have a cosine within the integral there. So as a reminder, when you see sine squared, you have to use that double angle for cosine identity substitution. So if you remember that cos of 2x is equal to 1 minus 2 sine squared, if you rearrange this for sine squared, you'll be left with an expression that you can integrate. So rearranging this, you would get that sine squared equals 1 minus cos 2x over 2. So when I come over to the integral over here, I'm going to integrate from 0 to pi this expression, and I'm actually going to separate it to get 1/2 minus cos 2x over 2 dx. Okay, so now that I've written in this form, the integral will be 1/2 x. Integral of cos is going to be, in this case, negative sine. So negating negative sign makes it a plus. Now, remember, if it's sine of 2x or cosine of 2x here, you're going to divide by the inside. So you have to divide the outside by 2. So it's going to be plus sine of 2x. Since there's already a 2 down here, now it's going to be 4. So my integral for sine squared, if you look back in your notes, should be this right here, 1/2 x plus sine 2x over 4. And we're going to integrate from 0 to pi. So when I plug in the upper bound of pi, we get 1/2 of pi plus sine of 2 pi over 4. And then from that, when I plug in 0 for x, I know this becomes 0. This would be sine of 0 over 4, which is also 0. So plugging in 0 for these expressions winds up yielding 0, so I don't really have to subtract that at the end. In fact, sine of 2 pi is also 0. So since this becomes 0, the total area from 0 to pi under sine squared x is pi over 2, would be the final answer to number 1. But I think the whole trick is remembering that we have this substitution from the double angle identity to make there. Once I do that, integrate, plug in the bounds. Moving on to something like number 2, this is going to be a good application of fundamental theorem. So when we integrate, we're going to plug in that upper bound for t, but then we have to remember that we have to multiply by the derivative of that bounds using that chain rule idea. So the derivative of tan is sec squared times the square root of 3 minus tan squared x. So the derivative of this accumulation function would be plug in tan x for t, but then also multiply on the outside by the derivative of tan, which is sec squared. So that goes pretty quickly as long as I remember that rule and how to apply the fundamental theorem there. And taking a look at something like number 3, we have 4x over the square root of x squared plus 1 dx. It's a definite integral from 0 to radical 3. If you want to integrate, this is a good example where we would want to use some u substitution. If you identify that our u should be x squared plus 1, that's a good u to choose such that our du becomes 2x dx, which is really close to what we have up in the numerator, except we would need to double the du to get 4x dx. Okay. So I'm going to pull that 2 on the outside and find the integral of 1 over radical u du. This is u to the negative 1/2, so up it by 1. And then, so that's now 1/2. And then divide out front, so that's the same as multiplying it by 2. You're going to get 2 times 2u to the 1/2. And notice how I didn't copy these bounds over. These are the bounds for x. So you want to make sure that you either at this stage in the game re-sub in x squared plus 1 right here, and then keep the bounds the same. Or you've seen me do this a bunch of times where you change the bounds by plugging in the lower bound and the upper bound into your U substitution here to get bounds with U. And I kind of like that a little bit better, to be honest. So if I plug in 0 for x, we're going to get that U is 1 for the lower bound. And if I plug in radical 3 for x, radical 3 squared is 3 plus 1 is 4 for the upper bound. So this is going to be really 4 radical U from 1 to 4. So we're going to get 4 radical 4 minus 4 radical 1. So that's going to be 4 times 2, which is 8, minus 4 for a final answer of 4 there. I have nothing against, of course, you using x squared plus 1, resubbing that in for U, and then just using the original bounds. You will get the same exact answer. Okay, so if we're good with number 3, this is going to be a real quick one. The last thing I'm going to do with you is the top of this page, which is identical to some review from an old set of notes, finding the value for these 3 integrals right here. If you remember what was going on graphically from 0 to 1 for the function x squared, the area would look something like this. If you sketch the area from -1 to 0 for x plus 1 squared, well, we know that that's shifted to the left 1 unit. So now it's this area right here. And finally, for x minus 5 squared, from 5 to 6, that's this area right here. And my sketches may not do this justice, but because these are all transformed versions of the function x squared, and the bounds are adjusted accordingly to find that same exact area underneath the curve, these should all come out to be the same. And just to show you what they are, equal to the integral of x squared is x cubed over 3 from 0 to 1, gives you an area of 1/3. You would confirm for the other 3, finding the integral, and then plugging in the appropriate bounds, that you get 1/3 for each of those as well. U sub would make your life pretty easy for the other 2. So as a reminder, in general, if you're integrating from a to b the function f of x minus h dx, you can think of that as integrating the original function f of x, okay? Go back to the parent function, essentially, as long as you then subtract h from the bounds. Or if you have the integral from a to b of f of x, and you want to figure out what are the new bounds for f of x minus h dx, well, remember that this is really technically, I guess, if it's x minus h, a shift to the right. So since it's the right h units, you would do a plus h and b plus h for the new bounds on that integral. So if you notice that you have some sort of transformation of a function that's easier for you to integrate, you can always apply one of these rules to be able to calculate the area underneath that curve. And at this point in the lesson, you'll see that the rest just says practice/review. So I'll encourage you to look through these, try as many as you think you can get done by the next time you're in class. And then when you're in class with me next time, I'll give you some time to work on these in small groups so you can collaborate with some others, get as many done as you can, and then we'll go over them before we leave class. So if you have any questions as you're working through these, let me know next time I see you. Otherwise, have a great rest of your day.